download, not that. We've got the Australian standards for shaft design. And our formulas and graphs and stuff are going to be coming from there. So go ahead and download that, or else you'll be lost. All right, so once you got that open, have a read through it. This is all the definitions for the terms that they use. This isn't the latest one. This is from 1985, but there's only been one other revision in 2004, and it's pretty much the same, just a little bit neater, and some of the terms are updated to like modern day English. And I think it costs like $120 to get the newer one, and we haven't got that yet. So we'll be using this one. All right, to start off, you can read through all of these. This is just like a guide. And if you scroll down to page somewhere, page 18 or page 20, not including the title page, it gives you a flow diagram of how you want to do this. So this is, you start off by evaluating your moment forces, so your moments, your axial forces, PQ, T's, your torque, and these would be your forces. Sorry, your factors. So this is your safety factor, and this is your endurance limit. We'll go through it. Okay, my video's not working, is it? What happened there? Give me a sec. Yeah, that's straight enough. Cool, shaft tutorial. So to start off, we need to pick the right shaft diameter calculation. And what we go to is you go to page 2, or table 2, page 8, table 2, to find correct formulas.
Is this shit?
Oh, jeez. All right. So the one that you choose depends on the kind of use that you have. So you would refer back to your JDR document, which I'll have.
7:30. Yeah. Not much. Yeah.
I'm just gonna mute you. All right. So looking at the operation, it says you can guess how many mechanism starts per year. So how many times will this shaft start? And because we're only going to be operating this for 6 months, you can assume that it's not going to be starting like 5 times a day or whatever it is. So you nail that down. So it's one of these two. It says number of revolutions of shaft per year. It's going to be under 900 or it's going to be over 900. It's quite a small shaft, I'd say. And just like as a guess, you can assume that it's going to be greater than 900 because it's going to be spinning at what, like 1800 RPM or whatever it was. You can assume that it's definitely going to be over 900 revolutions. So you can highlight that one and write it down. So D3 T4 times F S F R squared K S K MQ plus PQ D 8000 squared plus 3 on 4 TQ squared. We'll just go through what each one is. D is going to be your diameter. The FS, safety factor. And what was the safety factor we've been using for the past couple of tutorials? It's 1.2. FS. FR is going to be your endurance limit. Endurance limit depends on the tensile strength of the material of your shaft. So, and that's so once we pick a material, you can get that value. KS is a size factor. So the bigger your shaft, the stronger it's going to be. And that's in page 9, table 1, or figure 1. And that's that one there. But we'll go through it soon. K is going to be your stress raising factors. And this depends on the components or the characteristics of your shaft. So let's say you want to attach a gear to a shaft. There's different types of ways that you can do it. Either it can be like a spline, it can be like a keyhole that you cut into it. It can be like a transition fit or a tight fit. And those are from figures 3 to 10. MQ is your bending moment. Depending on what point of the shaft that you're looking at, it's going to have different bending moments and forces acting upon it. So you have to calculate that. PQ, axial forces. Again, you have to look at what's going in and out of your system. You calculate that shit. D, diameter as well. TQ is your torque running through. Torque running through shaft.
Yeah. How about nice socks? Yeah. How about lens? It's copper.
Cool. Right, to start everything off, we need to have a better look at.
They're free.
Nice. Jeez, that was loud. We have to have a better look at our shaft A. So to isolate it, I want to take it out of the whole system. Sorry, I turn it off. So This is a crappy drawing of the pulley. Oh, that's horrible. And then that'll be your first bearing, and that's whatever. Let's say that's your gear, and this gear attaches to, or it mates with the motor's gear. And that's your second bearing in your second stand. Second, first, doesn't matter. Cool. Not to scale, obviously. And you start off by determining your axes. X, Y, Z. X positive, Z positive, Y positive. None. So the process, I like to write it up before doing anything. Locate your critical points. So these are the points in your shaft that are most likely to break. Calculate forces. Stress raising factors.
凡事不要慌，这把手就拿出来拍朋友圈。
Everyone's noisy today. And then calculate diameters. Alright, first, going back to our diagram, we know that there's forces going in and out from the gears and from the pulleys. So we have to calculate them individually at these 2 points. So gear forces. So we know that gear A, gear B, and from the first tutorial's answers, this is a TS672, TS612, I believe. And there's a pressure angle that they meet at, and there's also forces going in and out. Right? We've got to isolate these forces so we can find out the exact forces from the motor driven through the gear, as well as the weight of the gear itself. So there's an FT, and there is an FR. And the FT and the FR are the reactions from this gear. And there's also FGW, which is the weight of the gear. And the equivalent force of that is simply FGY, FGX. All right, we'll start off with a simple one. FT or FGX because there's only one. FGX equals FT.
Yo me subo. Wow.
I'm gonna mute everybody that comes in. Cool. All right, and FT is simply the torque divided by the radius. And the radius is just half of the diametric pitch of the gear. And for a TS672, diametral pitch was like 46, I think. 46.567 per 2. And the torque is 2604.35. That's also from the previous tutorial. So FGX is simply 2604.35 newtons divided by 46.567 times 10 to the negative 3. Yep. Times half, because we want the radius, not the diameter. Cool? Equals 111,854. Make a note of that, because we're going to need that. So that's the horizontal component, or the horizontal stress resulting from the gear input. Next, FGY. Because there is a relationship between FT and FR, which is a pressure angle, and the pressure angle of the gears that we choose is 20 degrees. So the pressure angle is the angle at which the gears should meet. Should be put together at. So FT tan 20, because you can imagine that as a right angle triangle. So tan 20 FT is FR, right? Minus FGW, which is the weight of the gear. I need more space. I rewrite. So FGY equals FT tan 20 minus FGW. And for FGW, for the TS672, from the gear catalog, there's information on the TS672 that tells you that it's 70 pounds. So from freedoms to newtons, you would go 70 divided by 2.2 times 9.81, and that'll give you 312.1 newtons. Remember, that's from the gear catalog. Whichever gear that you choose, go there and find the weight of it. So 111,854, 10, 20 in degrees, obviously, minus 312.1 equals. I've got 4399.4 newtons. Cool. So that's our forces at that gear. What do you mean? What do you mean by two different types of pounds? You mean like UK currency? And ignore my question then. Pulley forces. All right. 1, 2, 3. So with the pulley, there is two forces resulting from the operation of the belt, assuming that it's rotating this way. Pound force and pound mass. Yeah, pound force is that's a force unit, and pound mass is just like the weight of it. So if this is the driving pulley and it's rotating anti-clockwise, which side is the slack side? Which side is the tight side? Anyone? I just think of it as like if you're riding a bicycle and you're going this way, this is your driving. You don't have to draw this, by the way. Then if you're pushing your legs and it's going anti-clockwise, that side is going to have more tension and drive the back wheels. Cool. All right, what other forces are there in the pulley? Are there any others that you can think of? Anyone? Not so much, but good thinking. I don't think that the friction will have a meaningful impact on the shaft itself. Yeah, wait. FPW. And our equivalent 6 FPY FPX. So we have to split our F1 and F2 into vertical and horizontal components, and then do a force analysis, force of equilibrium, and find FPY, FPX. Very fun. All right. Yep. F2. So I write this as F1X and F12. Oh, sorry. Y. Same as F2X. F2Y. So I write this down so I don't get confused about the directions. We know that it's always going to be pulling to the right because the two pulleys have two forces that go to the right. So these two will be in the same direction and these will be opposite, but varying in magnitude. So the critical component that we need is this, and these are going to be the same unless you have a offset pulley system, which is weird, but don't do that. So it'll be the same as your contact angle, sine -1, t minus d, 2c. And this is different than the contact angle that we used last week. So we're actually only concerned with that angle, because that angle corresponds with that. Cool? So use that one instead. So we know that
Can you
from
pull
last
the
week's
page
tutorial.
down a bit? Thanks.
So from last week's tutorial, we decided that we wanted a poly A5. I'll just screenshot that too. Shafts, no friction, yes. So right, this page is going to be crucial. So if you haven't downloaded the answers to last week's tutorial, go and do that. That's going to be what you need. And where's the diameter? There. That. So we need the smaller diameter, 340. So small d equals 340. And the larger diameter, which is the one attached to A, is 1020. C is going to be the same. C is 1500. And while we're here, we might as well grab the F1 and F2. F1, 10876.7 newtons, and F2, 1684. Oh, and the width as well. So the width is 0.32 meters. Sweet. Everyone got that? 340, 1020, 1500, yada, yada, yada. All right, splitting it up again. F1, yep. F1x, F1y. So Sokatoa. Yes, I still use that. F1x, that's going to be, oh, we haven't done that yet, have we? Theta equals sine -1, d minus d on 2c. But you've got to convert that to degrees because we're going to be using sine cos 10 here. So to change that to degrees, it'll be 180 on pi. And what you should get is 13.1 degrees. So therefore, to get F1x, the adjacent, you'll use F1 and then cos whatever that angle is, right? So 10876.7 cos 13.1 in degrees. I'm getting 10,593.6. To get your vertical component, F1y, F1 sine theta, 10876.7 sine 13.1 equals 246.5.2. And it's worthwhile to mention that these are going that direction. And that's going downwards. Cool. Similarly with F2, F2y, F2x. I'll start off with x first. F2 cos theta. And those angles are going to be the same too. And that should be 1641. Units. And then F2y, F2 sine theta. Sine 1684.9 sine. And that's going left. And this is going up. So we've got the vertical and horizontal components of the pulley. We just need now the weight of the pulley. And for this, we're going to need some assumptions. Let me know if I'm going too fast. So weight, FPY, sorry, FPW. We can say that's the area pi r squared times the thickness B. We've got that already. Times density times G. So we have to assume a material. So if we assume that it's in, what have we got here? AL 2014, AL 2014. You can Google that to find the density of it. Rho equals 2800 kilograms per meters cube. Right? And that's just the radius of the pulley. And we know that the diameter is 1020. So half of that, PW equals pi 0.51 squared times 0.32 thickness of the gear, or the pulley, sorry, times rho 2800 times 1. You should be getting 7182.4. Which is 700 kilos, by the way. Sweet. So the reaction forces at the pulley in the x direction are F1x plus F1y. Sorry, F2x. That'll be 10,593.6 plus 16. That's going in the negative direction. Same with FPAY. We've got F1y plus FPW minus F2y. Yep. Make sure you get the directions of these correct as well. So obviously I'm taking downwards as a positive. That's why the weight in F1y is going downwards, so that's positive. But F2 is going against the other two, so you know that's a negative. Two, 4, 6, 5, 2 plus 7, 1, 8, 2.4 minus 3, 8, 1.87. Why is the sum going to the left? It's just because I determined that the first part. So I'm writing this as equal and opposite to that. That's just an assumption. You can have it negative as well. Just make sure that you remember to keep it negative for the next part, which is where it can get confusing. All right, to summarize. Gears or forces at gear FGX, FGY. What have we got? I've got 854 going this direction and FGY 4399 going up. And F at pulleys, I've got FPAX, FPAY, 12, 2, 3, 4, that way.
and then 9256.53 going downwards. So if the force is going that way, then the reaction is going to be going the opposite way. So we need these to find the reactions at the bearings of our support system. And to do that, we have to split our forces into X and Z components, and also Y and Z. So XZ, YZ calcs. So we've got to find the bending and the torque diagrams of both. So shear and moment diagrams. Start off, X again. So this would be a side view, sorry, a top view. I made that too big. That should be X. So I want the X positive to be going that way. So let's pretend this is your bearing. This is your gear. This is your second bearing. And this can be your pulley. And then that's your shaft. The dimensions for these can be found in the JDR report. There's a lovely diagram in there. And this would be 1586.75. If you can see that. The next one, I'll write it bigger. 71.75. And the last one is 125. Obviously not to scale because I don't ever do that. Next, you want to find your bearing reactions. Just as the basis, I'll put them as positives. So FB1X, FB2X. And we know that the reaction of the gears at the shaft is going to be negative. Because think of the gear at the motor pushing up, so the reaction of the shaft is going to be negative, right? So FGX, and same with the FPAX. Sweet. So now we can do our equilibriums and find the reactions. Have I lost anybody yet? Or does it seem like first and second year math? Moment at, let's go B1. It'll be there. So our first one's going to be FGX. FGX 1586.75. And then B2X is going to be positive, so FB2X. And then that plus that, I've got it as 1658.75. Just adding these together. And the last one is negative, so FPAX. And the sum of all of those is 17. 3.5 equals 0. So we have that and that. Put them all to the other side. B2x there. So FGX would be 111,854 times 15,8 plus 1223 4 times that is 16. Sorry, 0.75. And that should give you 120.71. So that's your first reaction. And sum of forces again to get your B1x. X 0 minus FGX plus FB2X minus FPAX equals 0. FB1X equals 3917. After that, we'll need to draw a rough shear and bending diagram so we can find the bending at your critical elements. So first your shear, if I remember how to do this. The first one is going to be 1397 up until your first gear. Sorry, your gear. It's only one. So from there to there, you've got a shear force. That's a nice line. That's 0.5, 1.5. Just a little bit further than that. That's 2. And then it goes down by FGX. I'll write it down clearly. FGX equals FPY equals FPX equals 12,234 roughly. So 3917 minus FGX minus 107. It's pretty much 110. Down. I'll label that. It goes across until the second bearing, which is like 70 mils. 107,937. And then you'd go up by your bearing 2, which is 120, plus 120, 171. So that's 12,000. 1, 2, 3. Beautiful. Does everyone know what I did there? Does anyone remember how to do a shear and moment diagram? A little bit? Not really? Yes? Kinda? So what do you do next? How do you do a moment diagram? So a moment diagram is pretty much the area under your curve, or in this case, a box. That's pretty simple. Integrate? Nah, stop that. I don't want to integrate anything. I'm not about that life anymore. Math integration and triple integration can stay in math mod 2. So this is newtons and this is millimeters. This would be Newton meters. This would be millimeter. Or let's make that meters, sorry. Just for consistency. 1, 2.5, 1.5. So the way I do it is 3917 times your distance from there to there. That would be your first point. 3917 times, so 15862 meters, I think, is 1.58675. So you should have a lovely 6215. Oofed. And then the area under this part times by that distance. So that value is 107,937 times 0.07175. So you would take that and then subtract that point by this. So 6215 minus, that would be negative 1530. 29.5. And then last point would be closing it up. Beautiful. And that's going to be key to doing the last part. Is everyone following? Because next we have to do the YZ. More fun. Okay. YZ. I'm trying to save some space. Okay. For the YZ, your axes. Z positive, Y positive. So then your first bearing, gear, pulley. So set up the bearings the same way. FB1Y, FB2Y, and the direction of the gears is going to be the same downwards, or in the direction at least. but your pulley, because we have an 800 kilo pulley, the reaction is going to be that way. Dimensions the same. 15, 8, 6.75, 71.75, 125. I should get a stamp. I should get a stamp that says not to scale. So I'll write that on it. Moment at let's go B2 to spice it up. All right, if that's positive, then FPY is going to be positive too. FPAY 125. If FGY is going to be positive too. What did I do there? Yeah. Minus FB1Y. And that'll be like that plus that. So 71.75 plus 1586.75 equals 0. So we have 1, 2, FB1Y to the other side. FB1Y equals what were those? 40, 309. 9256.5. So we have these two, put them on that side. 9256.5. I think that looks right. How's the camera quality today? Is it shoddy? Y. Sum of forces in the Y is going to be 0. Shit. Yeah, it's because I paid premium for the camera app that I'm using. $5. $5 for an app. FB1Y, FB2Y minus FGY plus FPAY. I'm not going to remember to do that. I claimed a pair of wireless headphones because I said I'd be using them for tutorials. Don't tell ScoMo. So we have that, B2Y for the other side. minus 9256.5. Yep. And then minus FB1Y. I'll write that on another line. Equals 28697.1. Yeah. Ugh. Similarly for this as well, paragraph's going to be looking a little bit different. Shear. So if you're going to do it this way in the assignment, label your axes, be better than me. 2, 1.5, 1.5 meters, newtons. It's the first one up until the gear is positive 2445. Oh. And then you would subtract. Yeah, you would subtract FGY, which is a lot. 2445.4. That's 38,000. If you can see that, 37953. And then the addition of your bearing 2 reaction, which is going up, but not all the way. That should be 9256, 9256.5. Bending YZ. Let's pretend that these two lengths are the same. 0.5, 1, 1.5, 2. So that times the distance would be 2445.4 times 1.58675. Clean line. That's critical. And you would subtract the next part, which is another line, minus 379536 times 0.075, 7175. That's not right. 379536 times. That's better. I've got oh, 1156.83. Your answers are going to vary a little bit, but like maybe like under 5%, because everyone uses different numbers of decimal places. I'll stick to 2 if I was you, and you can be consistent. I'm not consistent at all, but you should be. Anyways, so you've got the bending moment at 2 points, at the gear and at the bearing. That's where it's going to be the max. So we can find 2 different maximum bending moments if you put them together. So MQ, which we decided was bending moment, MQ at gears. So if we have X and Y, we can put it together into a total by squaring it. Squaring the root. I'm going to write it as MQG, MQ at G, which was MQGX squared. So the moment at the gear in the X direction plus MQGY squared. So you root the square. And the first one we calculated was 6215 plus 3880. And your answer is going to be around 7324.4. And similarly, MQ at B2 see B2X plus MB2Y. Eleven five six eight. And the other one is 15295. And because you're going to square it anyway, it doesn't matter if it's negative or positive. You should have around 1919.8. Cool. We have 20 minutes. That's not too bad. Does anybody have any classes like at 1:30 for another subject? Cool. So we have to do this in 2 steps. We have to find the minimum diameter at the bearing 2, and the minimum diameter at gears. And there's a couple processes for that. So we go back to our diameter equation. We find out what we do have and what we don't have. We figure it out. Off the head, 10 to the 4 F safety factor. FR, I think. Yep. Square root of KS size factor times K. MQ plus T PQ D 8,000. All right, what do we have? For FS, it's going to be 1.2 because that's the standard we've been using for the tutorials, so that's constant. FR, we're going to use the same material as the JDR report, which is a 1030 cold rolled steel. Yes. And the tensile strength is 831. Let me check. 848. Sorry. So it'll be 0.45 times that tensile strength. Got 381.6. Should be megapascals. So tick tick KS we don't have yet, and K is going to be the complicated one. So going back to your shafts standards, K is found. Wake up. K is found in pages 11 to figures 10. And that's all depending on how you want to attach that component, that particular component, to the shaft or whatever else you have. So let's say, for example, you have a step shaft. So the step shaft is where you have two differing diameters, and the way that you connect them is through a radius. So there's no such thing in real life as a straight 90 degree. There's always going to be a certain radius depending on what tool you've got. So if you have that, you would find out what radius you have, find your correction factor, take it to the next page to find your Z, compare it with your tensile strength, and then you'll eventually get a K value. All right. So you would plug that in, put into there, find out which line you've got, and you would start off with around there because your tensile strength is 850, and then go left, and that would be that. Other characteristics you can have in a shaft could be like these keyways. They're pretty neat, but they're hard to machine. So depending on what kind of fit you have with your gear, you would have to have a keyway for the shaft and a key slot for your gear, and you just slot it on, and then it drives it, and it's pretty cool if you can get it right. Same here, you would look at either transitional interference fit, H7S6, H7K6. That's the kinds of fits. Or you can have a double, and that's super cool. But I'm just being a nerd. What else is there? There's splines too. If anyone knows what a spline shaft is, they're used mainly for like driving applications with steering. Yep, depending on what kind of splines you have, you would go to the material of the shaft that you're machining, go up, and then put it. I'm pretty sure involute spline is if your spline teeth aren't mirrored. Don't fact check me on that. There's also stress relieving grooves. So if you have one of these grooves in your system, you just go to this table and look at it. And one other one is a stress raising factor for transverse holes. So things like what do you call them? Like set screws to put them in. So if you have that shaft and then you put a gear around here and then you slide a shaft through there, which you'd have to machine a hole through your gear too. I don't particularly like that, and that you just use that. But for this instant, for this tutorial, they don't actually specify how they want to fit the gear onto the shaft. So our K is going to be 1 because not specified.
Did that make any sense at all? You look at the kind of fit that you want for your component, and then you find your stress raising factor, because if you have a more complicated or more destructive, as per se, mounting method, your factor is going to go up and you're going to have to compensate that and make it thicker. Sweet as. So what else have we got? Okay, we don't have KS yet. We'll come back to that. MQ, yes we do. MQ is either 7324.4 or 1919.8, depending on what you're looking at. PQ is going to be 0, so that term can be crossed out because you don't have any axial forces. You would have axial forces if you used like helical gears, because there's a horizontal component to how you'd use that. Then you'd have to change your bearings to what are they called? Axial bearings, I think. The name's slipping me right now, but the gears that are allowed to take forces in the axial direction. But we don't have any in this circumstance. And TQ is 2604, and that's from the previous tutorial. So the only thing we need is D and KS. So this is when you're gonna have to guess. So the way that people do this is they guess a value and then they compare it to a table, and which it'll give you a KS. Then you would go back, calculate that, and you compare it to your answer. And if it's within a certain tolerance, then you can use it. But if not, you have to recalculate it again. So I'll demonstrate. So for gears, gear diameter, or I should say shaft diameter, shaft D at gear, your initial guess, let's, someone pick a number, any number, or between, let's go 50 and 150. All right, let's go 53. Initial guess, D equals 53. So you would take that, shove it into your figure 1, which is your size factor graph. If you can see my mouse, 50, 60, 70, 80, 90, 100, yep. So 53 would be around there. You'd go up to where it hits the line. That would be 53. I'd say 1.46. Yeah, I'll go with that. KS equals 1.4. What did I say? 65 from figure 1. Right? So your initial guess is D, and you use that, shove it into the table, and get KS. Then you would have all the values to find your minimum diameter. D cube 10 for 1.2, 3, 8, 1 point something, 6. And then finishing this off, we had our size factor 1.465. Stress raising factor is 1 because it's not specified. Times at the gear, the moment is 7,000. So 7,324.4 squared
plus 3 on 4 TQ squared, so 2604.35 squared. Just do that. One point 4.5. 2604. Sweet. I've got 66 millimeters. That's your answer 1. All right. From this step, we have to compare our calculation to our initial guess. And what we want is a minimum of, let's say, 1 to 2%. Let's go 1% variance between these two. And because that's heaps, we have to reuse 66 as our guess and find another guess value, shove it into the formula, and get another D. So not within tolerance, therefore retry using D equals 66 as guess. So D equals 66, therefore, or DI, therefore KS, your size factor, 66, that, 1.54, 1.55. Yeah, I'll go with that. 1.55. Therefore, D, I'm getting hungry. 1.2, 3, 8, 1.6, 1.55, 7324.4 plus 3 on 4, 2604.35. Yep, that looks okay to me. Times square root times 1.2 66.63. Answer 2. So this is your second iteration of that formula. You can see that it's around, what is that, like 6%? Less than 1%. It's around less than 1% variance. Therefore, it's okay. Oops. Cool. So that's how you find the minimum diameter if you have that much bending moment, forces, and that's your material too. So therefore, min diameter at gear is 66.63. And you do the same at the bearing 2. I didn't do this here. Yeah. And should I do it? Isn't it 3 minutes? Whatever, I'll do it. Alright, let's do it quickly. Min diameter at B2. So your guess, so DI is, let's go 60. So KS equals 1.5. It's quickly doing it. So rewriting your formula. 10 for 1.2, sorry, 2, 3, 8, 1.4, square root 1.5 times. So the moment at bearing 2 is 1919 squared plus 3, 4. Torque's going to be the same too. I've got 46.8, and that's quite a while, quite far from our initial guess, so we'd have to do it again. Adio. Taking DI equals 46.8, KS yeah, let's go 1.5. 4, sorry. Yep. And you should have, from my notes, at least, D equals 46.59. And I'd say that's acceptable. That's less than 1% away from 46.8, which is what we started off with. So therefore, DG and DB2 equals 46.59. Cool. If you guys want to delve deeper into the process of doing this, there's heaps of more questions at the end of, in the appendix of the standards. So page 21, it sets up like a huge, was it like a three gear gearbox, and it goes into how to find the minimum diameters for the shafts within the gearbox itself. And it's heaps similar to what we did, but it goes into more depth. So you've got more bending diagrams if you're lost and you need revision on how to do that. But definitely have a read through this before doing your shafts quiz, which is in like what, 3 weeks, I think. Cool. That's your tutorial. Anyone have any questions? Anyone need me to go back to any other pages? Sweet as. Good luck on your quizzes starting Thursday.
See you next week or tomorrow if you come.